what idea this is close to? What other thing multiplies by?
Geometric series?
Okay, I see. Huh?
Factorial?
Factorial, right? So, but it would be completely wrong to say this is 5n minus 1 factorial. Completely, because how much does this step by? 5. And this would inherently step by 1. Okay, I love it. And there's no reason it would stop at 4. It would go to 1. Okay, I like it. So, somebody help me out. Help me out. Without doing any computations, just plug in shit in. Can somebody tell me what A1 would be for this series in here, for the sequence?
X over 4.
X over 4, I love it. Somebody else tell me what A2 would be.
X squared over 9?
No. X squared over 4 times 9. So the way this says, it says 4 times 9 times 14 up to 5n minus 1. So when n is 1, what's this?
1.
When n is 1, this is 4. So it says take 4 and multiply it by 5 more until you get up to 4. Okay. When n is 2, this is 9. Take 4 and multiply it by 5 more until you get to 9. 5. So what would A3 be?
X cubed over 4 times 9 times 14.
Yeah, exactly. Okay, cool. Now, let's take it to the extreme. What's AN? And AN is a silly freaking question to ask. If you're doing the web advisor, they will ask you what AN is. You just copy the shit down. I don't know. So what's AN? Easy ass question. But it's this crap, right? 4 times 9 times 14 times 5n minus 1. How many elements are here is dependent on what n is. Right? If n is 3, I have 3 elements. So if n was 80, I would have 80 elements, right? It just keeps tacking on the next dude up, stepping by 5. So a factorial, like 7 factorial would start at 1. I could do it backwards. And then I multiply by the 1 up, 1 up, 1 up, 1 up, 1 up, until I get to 7. This one doesn't go by 1, so it doesn't get its own little symbol. Poor little dude. So we just have to write all that shit out. Okay, so what would an plus 1 be? I'll do the top. Okay, oof. I did half. What would that? Sorry. You think you're funny, math boy. All right. What would the?
It would be starting at 9, yeah?
No.
It would be 4, 9.
It always starts at 4. It's what it says by the definition, right? You just keep multiplying by the next thing up. So 4 times 9 times 14 up to this times, what's the next thing up?
5n.
No. Nope. You can do it 2 different ways. Let me do it the by the textbook boring ass way. And then let me do it, isn't this always 5 up? 5 up? What's 5 up from 5n minus 1? What's 5 up from 5n minus 1? 5n plus 4. Isn't that what you get when you do this shit? Okay. Maybe? So you're plugging an n plus 1 in to get the n plus 1 term will always freaking work. But the pattern will also tell you what the hell's supposed to be next. Now, do you see how when you set up the ratio test, a lot of shit cancels, right? In fact, all of this is going to cancel with all of this. And you're going to be left with that. Do you guys see that? If you don't, it's okay. You can say, no, I don't see your point, Jeff. So, real quick, I might as well bring this up now. I had a really good discussion with a student earlier in the Math Study Center. So, if you have a question, trust me, at least half the class has the same question. Just everybody happens to be a little quiet, right? So you could be their hero if you just ask the question, right? if just for one day? Any Bowie? No, okay. I live off of questions. If I ever make it feel like I don't, I'm sorry. I love freaking questions. I live off of the what if. That's some cool shit. What if? Oh, I don't know. Let's find out. Let's see what happens, right? So I don't want anybody to feel, if I'm doing all these things and you have a question on the second step and I'm on the 20th step, ask the question. Why would I get angry? I want everybody to understand every step. The whole thing is a learning experience. Just because I left the second step behind doesn't mean now you must know it, and if you don't, too damn bad. No, right? FML, no. Is that still a thing, FML? Yes? Okay. Yes?
So you said it can't be factorial if it's not increasing by 1. So if there's anything next to the n, it can't be factorial? Like if there's a 6?
No, because I could do like this, for example, right? Which just means if n is 6, this would be 16 factorial,
Oh, okay.
right? What this is doing is it's concretely stepping by 5. And then this is how it captures each one of these. If n is 1, you get 4, bam. If n is 2, you get 9, bam. So that is the nth term of this sequence of products. So you have to write them all freaking down for the nth term. So the n plus 1th term will have one more freaking term. It'll have all these same terms times the next dude. That is fundamentally what this is defining. What goes on the bottom? We saw it here. 1 term for the first, 2 terms for the second, 3 terms for the third. N terms for the nth, n plus 1 terms for the n plus 1th. Okay, maybe. So factorial is still relatively new, and then we throw this thing, which is sort of like factorial, but not. Factorials kick so much ass because I can just write them like this. I don't have to write them like this. Could I? Could I write them like this? Totally, right? So I could create something that was x to the n over, when n is 1, I get 6, right? When n is 2, I get, well, let me not do this. This is weird. So it would be something like 1 times 2 times 3 up to 2n plus 4. That would be 2n plus 4 factorial. And then if I wanted, so that would be like an. So an plus 1 would be x to the n over 1 times 2 times 3 times 2n plus 4 times 2n plus 5. Right. In fact, let me do this very concretely. Hopefully that's enough for you guys. If you have this written down, you just do the limit, the ratio test now, right? And a lot of shit's going to cancel. It's going to be really, really cool. So watch this. Let me take this over here. So real quick, let me just create something more straightforward. N over 2n plus 4 factorial. That's an. An plus 1 would be n plus 1 over 2n plus 5. Plus 5. N plus 1 would be 2n plus 2 plus 4, so that would be 2n plus 6. Is that cool? Okay. And if I do the ratio test, everything's going to cancel except 2n plus 6 and 2n plus 5, right? Now, if I write it like, let's see, n over, how can I write this better? 1 times 2 times 3 times 2n plus 4, that's an. These are the same thing, you guys agree with me? Is that cool? Let me make sure it's cool, right? That's just writing exactly what factorial means.
Oh, yeah.
Factorial means this times 1 less, all the way down to 1. What would an plus 1 be? 1 times 2 times 3 times 2n plus 4. Now here's what gets a little tricky. If I put an n plus 1 in, don't I get 2n plus 6?
So you multiply it again.
All right. So some of you guys might notice the slope on your linear expression inside of a factorial actually tells you how many things you keep multiplying by each time. So if it's 2n inside, you're going to multiply by 2 terms each time. Okay, let me finish this and then I'll go back and explain more of what I just said. If I do this ratio test here, right? Limit, blah, 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 blah. I don't care about that shit. This goes to 1. Let's get out of that way, right? How would I make these work with each other? What would I have to do? I have to rewrite this like what? 2n plus 6, 2n plus 5, 2n plus 4 factorial, and then this shit cancels, yes? Do you guys see, before I write it down, if I do the ratio test on this, these are the same things, yes? So the ratio test better come out to be the same thing. I don't have any other. Here we go. So it'll be n plus 1 over 1 times 2 times 3 times 2n plus 4, 2n plus 5, 2n plus 6 times 1 times 2 times 3 up to 2n plus 4 over n. Up to 2n plus 4 cancels. I'm left with 2n plus 5, 2n plus 6. Same damn thing, yes?
Yeah.
Thank God I don't have to do this shit with factorials because they are easily defined. So I can just do it this way. A more compact form, yes? Compact forms kick so much ass. Unfortunately, not everything can be built with a compact form. I think I already erased the one we just did. If it's going not by 1, I can't write it with a factorial because it's not a factorial. Factorials go by 1, by definition.
What were you saying earlier?
Okay, here we go.
Yeah.
Let me show you. Okay. I'm gonna take all this shit away. Is that all right?
Yeah.
Okay. I kind of hope nobody's writing this down. Just absorb. So what I was saying earlier was this. Watch. What's A1? 1 over 6 factorial, yes?
Yeah.
6 factorial. So that's 1 over 6 times 5, blah, blah, 1, yeah? What's A2?
2 over 8 factorial.
8 factorial. How many more terms did I just multiply to get to this one?
2.
I just multiplied 2, right? 6 times 5 times 4 times 1 times 7 times 8. 2 more. What do you think would happen if I had a 3 there?
3 terms.
Every time I did that, I'd get 3 more terms on top. Do I have to worry about that shit? No, because it's factorial.
Yeah.
If it fundamentally goes by 1, any of that shit doesn't matter because I can deal directly with the factorial. That's why factorial is so nice. This kind of guy, this kind of poor little dude, doesn't have a factorial form. Right? We could create one. Let's not. Yeah, because then you would need something like maybe we could do this. Instead of an explanation with a point, the 5 would mean it goes by 5s. You see what I'm saying? So if I put a 6 there, it would actually go 4 times 10 times 16. And by the way, real quick, that's not very far off. That's sort of a drunk history of math, but it's not far off from the way it actually happened. I mean, somebody had to come up with this stupid symbol here for square root, yes? Aliens didn't come and say, use this or we will come back and destroy you, as far as I know. That is the very drunk history of math. We just had to come up with it, and somebody had to come up with it and go, hey, what about this shit? Let's make that mean half of the thing, multiplying, the other guy's got to go. Yeah, okay. And then somebody in the back's like, I don't like it, and they killed him, and then they kept going. All right? Thanks for listening. No, that's the extremely drunk history. Anyway, quick point. There was a lot of poisonings, duels, there was some subterfuge, there was some spying, there was some shit. There's a lot of shit in math history that people don't know. It's not quite Game of Thrones level. Like our season 8 would be better, for example. The game of math. but I'm sorry, I'll stop. Does that make more sense? I mean, the unfortunate thing is if you do have something built like 4 times 9 times 14, you just have to write it all out. The fortunate thing is a lot of it's going to cancel when you do the ratio. Yeah.
Could you write 5 times n factorial minus 1?
Let's see. You mean like this?
Yeah.
Well, let's try this out. So when n is 1, I get 4 here, right? When n is 1, what do I get here? I get 4. I love it. When n is 2, what do I get here? 36. When n is 2, what do I get here? 5 times 2 factorial minus 1. So I see what you're doing. You do get 9, but you're supposed to get 36, right?
Right.
Do you see? Because the second term should be both of these multiplied. Okay. By the way, what John just did is beautiful. Ain't a damn thing wrong with playing around with shit. Why the hell not? At this level, you are in Calc 2. And I feel really bad because pre-calculus is where we're supposed to start using language like, you got to play with this shit. Do you guys remember proving trig identities? Do you have fond memories of that? No. That was the first real direct time you just had to play. Part of the process was to pick the wrong thing to do and go, well, that was the wrong thing to do. You guys understand what I'm saying? If you remember it, you go, let me try this. Oh, all right, let me back up. That's playing around with shit. Let me try this. That didn't work. Let me try to work on this side. That didn't, you're just playing with shit. So the more you learn, the more you should feel free to play. You're like, is there a more compact way? Beautiful motivation to try to play with math. There's got to be a more compact way to write all this shit, right? Not really.
So if you had n factorial, because n goes by 1, right? But could you make it jump by multiplying n factorial, like the whole thing, by like 2, so it goes like 2, 4, 6?
So again, if you just did this, so this is like 2 times n factorial.
Well, I'm not sure if there'd be a difference, because 2n factorial is like different than 2 times n factorial in like parentheses.
Totally, true. But it doesn't do what you want it to.
Okay.
Yeah. But again, you can play around with it if you want to. All right. You guys semi-okay? I mean, there's a lot going on here, I know. This idea is so closely related to factorial that you wish there was a way to write it more compactly, and there just wasn't one created. If we wanted to take time, and let me give you a spoiler alert, we're not going to, we could try to create notation that would be consistent. That's the next thing. You have to define how it operates. You have to define how it kind of works with itself. Factorials, we totally know how they cancel and shit. Right? Okay, all right. Okay. Was that enough for that? I already erased it, so hopefully that was enough for that question. Anything else from homework stuff? No, okay. All right. It gets me concerned because I know some of these questions are weird. So if you're like, well, that's just weird, you're right. So I'm expecting questions on some of these. And if I don't get them, I'm like, nobody's doing the damn homework. Yes?
N factorial over n to the n for doing the ratio test.
Yes. Okay. Start at 1? Okay, thank God. Can you guys remind me, did we talk about this? Anybody remember what this was? You guys remember what that was? Yes. This is E. Okay. And I'm pretty sure we did discuss that. We did the logarithmic thing, where we took the log of it, then the natural log, we found its limit, we raised it to E, or E to it, right? We did that last time. This now is just a known fact, right? Okay, so now you're like, what's that got to do with this shit? Well, let's see. everybody out there, if you haven't done this problem yet, set up the ratio test for this. So Maddie, just hang out, I guess.
We were doing it in the math lab and it got all messy at the end, but yeah.
Okay.
Yeah.
Let me catch up to you guys. Okay. So where are we at with comfortability with how factorials, comfortability, is that a word? With how factorials interact in these ratios, right? Do you need to write it out, or can you tell me what's gonna be left over? Just an n plus one. And again, it would be n plus one times n factorial, because they keep going, so these would kill, so then they get an n plus one. Over this, and you should know what to do with that. Do you see how this is one n plus one and this is n plus one n plus ones? So how many n plus ones cancel? One, so then I get n to the n on top over n plus one to the n, because I lost one of them. So this is the limit as n goes to infinity of n over n plus 1 to the n. Now I know last time we talked specifically because of something like this. This. Can somebody please combine these for me? What would that be? N plus 1 over n, right? And that limit is e. How does this relate to that? This expression, that expression. This expression, that expression. How do they relate? It's 1 over it, right? So if this limit is e, that limit is 1 over e. So somebody was asking me earlier, if I do a homework problem and I do some work, and then later I have the exact same problem like show up, can I just shit, yeah. You say, look back at the work I did. Why would you have to recopy work? So very often you'll see something that starts off and you do the ratio test and you get down to like 1 over n square root of natural log of n or whatever, and you're like, well I did that earlier. Let me just reference that earlier work. Is that totally legal? So here, I'm gonna reference this known fact. Question, I'm gonna say this is 1 over which is 1 over e. That's an e, by the way. And the important thing is 1 over e is what? This is ratio test. 1 over e is definitely less than 1. It's 1 over 2 point blah, 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 right? So it's less than 1, so that means that this converges. I like it. I went too far. I was going to leave something for you to do, and I just couldn't stop.
Because he had done it like, broke it apart, n, ln, yeah.
I'm with you. No,
Yeah.
listen. This is hiding all the work it took to show this.
Okay, yeah.
And we did that work last time. We had to do a natural log, the n comes down, I needed to make it 1 over on the bottom, do L'Hopital's, all this kind of shit, yes? Please correct me if I'm wrong, I think we did that last time. Didn't we do that last time in here together? Now that we did the work, if I see 1 over this shit, I did all the work for this, all right, 1 over e, I already did the work, right? Now don't get too excited, you're gonna see stuff that's not quite that, so you're gonna have to actually do the logarithmic L'Hopital business, right? Okay, maybe. Yeah.
Can you do 46 from 11.6?
46. Oh yeah, this one. Okay. First off, this Indian mathematician, I used to know how to pronounce his name. I feel really bad I forgot because he did a ton of shit. If you just Google this man's name, you will find so many little things he did. Yes? And so look at this. This is such a beautiful, I don't know if you guys would use that word. This problem is number 46 just because it's got a load of shit in it. You guys agree with me? So let me put it up on the board if you're bookless. The plight of the booklets out there. So he discovered that 1 over pi can be represented as, pick the book up, Jeff. 2 rad 2 over 9801, 9801, 2, 0, yeah. Oh boy, this is going to get exciting. Old man alert. Let me see. What's it say? 4n factorial? Yeah, okay. Times 1103 plus 2690. Is it 2690? I left one thing out. 26390. Obviously, it's 26390. And over n factorial to the 4th. Now you should be asking yourself, how much time did this man have? 396 to the 4n. Okay. Now, this is obvious, yeah? No, no. Okay. The reason do you guys notice it's the big numbers and it's the amount of shit. It's nothing more than some earlier stuff we did. Could you write the n plus 1th term? Right, because I think the question says, verify that it's convergent. Yeah. Okay. So this, I can focus just on this. I don't have to worry about this guy. It's just a multiplier out front. Who cares? Oh, yeah, I'm sorry. Is this the one you wanted?
Yeah.
Who asked it? Oh, yeah. 11.6, number 46, yeah. So now you just have to write the n plus 1 term, do the ratio test. On the bottom, I would highly recommend that you write that 4 times, right? N factorial, n factorial, n factorial. So then you get n plus 1 factorial, n plus 1 factorial. So then you can reduce them each, right? Just makes it easier. Do you guys see how most of this is just window dressing bullshit? No? Isn't this just a polynomial? Does it really matter that's 1103? It could be 3. That could be 5, but it isn't. So it's not worse than 3 plus 5n. It isn't. We don't let constants bother us. Right? We're calculus. We don't give a shit about they come for the ride. Screw them. So just this piece. Want to be 1103 plus 26390 times n plus 1 on the top, and then the same thing, but that on the bottom. So won't it be the ratio of the highest degree, and that's going to be 1. The highest degree is going to be 26390. I don't know if you guys see what I'm saying. That is polynomial in nature. Ratio test is going to eat that for lunch. Not a problem. You just get, as a student, you look and you're like, holy shit, but that's linear. Who gives a shit? This is a single factorial. Not a problem for us. This is a factorial to the 4th power. Okay, we write that 4 times so I can keep myself straight, right? And then this is the 4n. So what would an plus 1 look like? And again, don't worry about him. He's not inside.
4n plus 1?
No? 4n plus 4, right? So it'll be 4 times n plus 1. Parentheses, it'll be 4n plus 4. And remember, real quick, remember what I said? When there was a 2 in front of the n, it slapped 2 things on at a time? Now there's a 4 on the n, a 4 in there on the n, and so it's going to slap 4 more things. 4n plus 4, 4n plus 3, 4n plus 2, 4n plus 1. It slaps 4 things on top of him. Is what I just said important to memorize? No, it's just an interesting observation. You can remember it if you want to, right? And by the way, just to really make sure you understand why there's a plus 4, I just replaced n with n plus 1. And then distributed the 4. I didn't have to know ahead of time what's going to happen. What does this become? because you replace n with n plus 1, you can distribute the 26, blah, blah, blah. Are you guys with me that this is not as big of a concern? Now down below, I would write n plus 1 factorial. I would write it 4 times just to kind of, or not if you get comfortable enough, you don't need to do that. And what's this going to be?
4n plus n, right, 4n plus 4.
There you go, yeah. Right, and then you do times the reciprocal of all this mess, and then a whole bunch of shit's gonna cancel. Right, and the limit of this piece to this piece, easy, same degree. Big ass numbers, I don't care. Yes? Yes, all right, and again, I'm not speaking like that, I don't mean to make you feel bad if you don't see this, because this is loaded. But you take one thing at a time. And we know how to do each piece of this. Is that enough to get you going?
Yeah, but part B got me confused.
Oh, yeah.
Like different places.
All right, so do 1 over pi in your calculator. And then calculate the value of this when n equals 0. That would be the first term, right?
Yeah.
How do you get the first term for the series? You let n equal 0. So they want to know the first term in the series times this, how close is that already to what 1 over pi is?
So this series is a proof that is equal 1 over pi? Is that what you're saying?
He did a proof.
For the
He
first-
proved that this series perfectly becomes this number.
Oh.
So you can look his name up. You can see he did a lot of shit. But he doesn't get as much recognition as he should, which is one reason why I assigned this problem. Yeah. I also assigned the problem because look at it, it's just too beautiful. Give me a break. You guys might use a different adjective, I don't know. I don't know, is that better? I mean, when somebody looks at that, you get overwhelmed. But then you start to realize, I know how factorials work. That's just a linear function of n, right? I can write him 4 times and he's no big deal. Each piece is easy as shit. This is, I could just increase the power. And now when I do this, I'm going to multiply by the reciprocal of this. So like the 396 part, what's going to happen between these guys? How many? 4n of them. So I'm going to have on the bottom, I'm going to have 396 to the 4th power left, yes? You guys see that? Okay. So huge thing about math is the more you can break it down to parts, the better you're going to be at it. Right? In fact, I mean, that's a life lesson, to be honest, but, okay. All right. Okay. Anything else from homework stuff? Or general questions? Okay, let's get back into where we left off. Oh, by the way, what's happening Monday? Quiz. 11.6, 11.8. So it's going to have just the basics of power series in there. When's their next test? A week after this coming Monday, yeah? So on Monday, I'm going to have the practice test, and then the following Wednesday will be review day, right? And then we have the beautiful test on May 1st. Okay. All right, okay, so last time we finished up section 11.9, but I do want to sort of take a step back and look at 11.9 one more time. Do you guys remember what this was as either an infinite polynomial or as a series?
1 plus x squared plus x.
Careful, yeah, 1 plus,
Oh, x.
yeah.
X squared.
Now can somebody figure out what that would be as a series?
Let's do that.
Yeah. N equals 0, I love it. Infinity. And when does this thing, what is the interval of convergence for this? Yeah, because this is just geometric, right? This is just geometric. What's got to be true about the base? What number can I pick and this would converge? The absolute value better be less than 1, right? Is that all right? So I like this problem. I like the book started with this because it's a perfect transition from shit we know to shit we don't know yet, right? Okay, maybe. So, can somebody please tell me what this is? Yeah, so it's going to be sum, if you want to write it in series form. You just replace x with what? So when I have an x here, there's an x here. So when I have an x to the 5th there, there's going to be an x to the 5th there. And of course, that just becomes x to the 5n. I love it. So this is just a function. What is the most basic rule of functions? Substitution. F of 2, put a 2 in. Why couldn't I put a 2 in? Why does this function not like 2? Because what's the domain of this function? Negative 1 to 1, right? So if I said f of 1/2, what would I do with the 1/2? Plug it in, yeah? And I plug it in. So then 1 over 1 minus 1/2 would equal the sum of 1/2 to the n. We know that from geometric series. We know that r is 1/2. We know. Okay, maybe. So if I want to know what f of x to the 5th, isn't that f of x to the 5th? I just plug an x to the 5th there. Or I could even write it as a polynomial. What would it look like? 1 plus, what am I plugging in? So 1 plus x to the 5th plus x to the 10th. Blah, blah, blah. Yeah? Okay. Okay. Not too bad, right? Not too bad so far. And then we did some stuff like we took the derivative of this, we took the integral of this. So let's do this. Let's work with a series. Let's take the derivative of the series, and let's take the integral of the series. Okay. Let me erase all this. So if I have this series here, what you got, Jeff? Oh, yeah. Sure. Let's make this n plus 2 on top. Sure, I like it. Right, so make it n plus 2 over n plus 1. I just don't want this first term to be 0. So that is my f of x. How would I take the derivative of that? What is this as far as the derivative is concerned? Constant, because I'm taking the derivative with respect to x. For every term, n is a constant. Yes? I like it. So this just comes for the ride. What's the derivative of x to this thing? What's the derivative of x to a power?
N plus 2
The power comes down?
times x to the n plus 1.
Pcas. So this, f prime, is the sum of n plus 2 squared over n plus 1, x to the n plus 1. Now, okay. I haven't put this here yet, but every time you take a derivative, this will start up one further. Let's double check this. Let's look at the concrete thing happening behind the scenes. So I'm hoping that some of you guys out there are like, okay, taking the derivative of a series. If you would have told me we were going to do that, I would have freaked. But compared to what you could imagine, isn't that much simpler? It's not the most straightforward thing in the universe, but the derivative, the rules are still there. It's all the same thing. The only piece that means shit to me is the x piece. Everything else is a constant, right? So it's going to be basically nothing but power rule. What's the easiest derivative rule besides e to the x? Power rule, right? Power comes down, goes down by 1. Okay. So can somebody, let's see, what are the terms of this? Somebody give me the first few terms. The first term would be what? You can do it.
3 over 2 times x to the third. Or, yeah.
I'm with you.
2 times x squared.
Yeah, 2x to the second, right? 0. Okay. And then it's going to be n equals 1, 3 over 2, x to the third. So you can do this for yourself. N equals 0, n equals 1, n equals 2. Let's just do one more. 4 thirds, x to the fourth. And of course it goes forever. Okay. Now let's write what, let's see, this says. When n equals 1, what do I get? 9 over 2. Have I lost one? Oh, this should be 0. In this case, yeah, okay, in this case, I don't lose a term. When n equals 0, is this 0? No. Okay. So when n equals 0, what do I get? I get 4 over 1, x to the first. Isn't that the derivative of this? Right? Plus. Looking at this, and then we'll look at that. N equals 1. So this is n equals 0. What's n equals 1? If n equals 1, what do I get? 3 squared, 9 over 2. X to the second. And that, of course, is the derivative of this guy, right? Okay. All right, maybe. So we did a problem the other day where it wasn't 0, it went to 1, because in that problem, when the n came down, it made the 0th term 0. Okay, so this one doesn't have that problem. So remember, you've always got, for any series you're looking at, you've always got this infinite collection to look at. So especially when you got these x's in them, you got an infinite polynomial. So when you're taking a derivative, you could actually, if you have time, write a few terms out, make sure it actually works. Okay, maybe. Yes?
So why did n plus 2 over n plus 1 stay the same when you took the derivative? Because are those constants or?
Yes, totally. What is this a function of?
X?
X, 11.
Okay.
Yeah. So, for example, what is this in the first term?
2x squared?
2. This
2, okay.
is 2. This is then 3/2. So every single term, it is a constant. So the derivative is not going to touch it. I like it. Maybe. Okay. So what if all right, let's take a step back. Has everybody got this? Okay. What if I instead integrate this thing? Let's see, integral f of x. And just to be really straightforward, I can switch the order of these because the integral's only caring about x and the sum only cares about n. And then I've got this here, which really puts it into your face that this is a constant.
So can you just pull it out to avoid confusion, or
What do you mean?
the constant, like n plus
You
something?
could pull it out here,
Yeah, like between the.
but you definitely
summation and
can't pull it out
yeah,
there.
not out there. Like
Yeah,
summation.
you can totally put it there if you want
Okay,
to.
for sure.
Okay, in fact, let's go ahead and do that. You don't have to, but you can. All right, so now that should be really, really, really straightforward. All right, so I got the sum, n equals 0 to infinity. infinity, n plus 2 over n plus 1. Why did I put, I don't know why I put parentheses. What does this integral become?
X to the n plus 3 divided by n plus 3.
11. Okay. And to figure out what this is, I'd have to be given more information, just like way back when, right? We are going to get to the point where we have to figure out what that C is. They're going to give us more information. Let's test this. Okay. What's the integral of 2x squared? The integral of this. What's the integral of 2x squared?
2/3 times x cubed.
Integral of 3/2 x cubed.
3/8 times x.
Yeah, so the x to the 4, 3/8, 11. So I like to do my little power first, and then I can do, so this would be x to the 5th, so then I want to divide this by 5. Blah, 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 right? Now let's see what this is. Please be right, let's see. When n equals 0, what do I get? I get 2 over 3, yes?
Yep.
So n equals 0, 2 over 3, x to the 3rd.
Yep.
Bam. Well, all right. Well, you guys can do the rest. Okay. So you can see the utility of operating on a series form, because you don't want to write every damn, because there's an infinite number of sequence elements. So let me just say, here's what every sequence element looks like. Integrate the form, and the series you end up with is exactly what it would be if you would have done each term. I don't want to do each term because there's an infinite number of them, so screw that. Okay, maybe. Yes?
So at the top there, like right behind you, you're taking the integral of a sum, and then you switch them, and then you're taking the sum of an integral.
In fact, are you ready for that? I love that question. This is perfect. Can you guys please, in fact, we just did it, but let me just do this real quick. What is the integral of 4x minus 7 plus 2 over x?
4x squared, 2x squared. Wait, 2x squared minus
2x squared, okay, wait. How did you get 2x squared? Why can't you do that by itself? Isn't this the whole thing? What do you never write, but you know is a rule? You never write this shit, do you? Does anybody ever write this?
Sometimes.
This is, sometimes? All right, cool, I love it. A man after my own heart. That is what you are doing. And there was a whole thing back in Calc 1 about you had to actually, that was one of the laws of integration, the fact that that was equal. Because you are finding the area under this minus the area under this plus the area under this, right? So isn't that exactly, look, so this isn't the sum first inside the integral? This one, isn't this the sum of integrals? No? Yes? So here it's the sum inside the integral, then it's the sum of the integrals. It's exactly the same shit we do to polynomials, and what are these? But polynomials. Okay, maybe. Okay, I like it. Yes?
I don't understand the point of integrating and differentiating the series. Like, what are we getting?
So, for example, let me go back to the very first thing. The only thing we know right now is 1 over 1 minus x, right? Even if you don't like anything we're doing, part of your brain must be saying, God, can I know something more than 1 over 1 minus x? Nobody? Anybody?
Yes.
So we did this last time. I almost said yesterday. What's the derivative of this? Derivative. What is the derivative of this? So we call this f. What's f prime? Does anybody remember we did this? Yeah, sure. Yeah, so there's a negative power on this, right?
-1.
But then there's a negative chain rule. So it's just 1 over 1 minus x squared. Is that cool? And now, instead of this fact, I really want this to make sense, because what we're about to do is we're about to create series for just about any function. This definition, we lucked into this shit. We completely lucked into this shit. We knew that if I had a geometric series and the r was less than 1, that it would be a over 1 minus r, right? If I put an x in place of r, I suddenly get a function. So there's our first power series representation of a function. We kind of backed into it. Do you guys understand what I'm saying? You don't totally, because you don't know what the process is yet to actually construct a power series. I just barely got into it last time. And I think most of you guys are probably like, brain fried, why doesn't he stop? Okay, which I totally understand. But now, what's the derivative of this? And now, of course, I could still say 0, but we just sort of go ahead and make it 1, because the 0 term would be 0. Right? So instead of actually having to do the full process of constructing what this is, I can just build it from what I know. So the more things I construct, the more functions I can create from those. So if I know what sine x is, which we will, how would I figure out what cosine x is? What's one way I could figure out what cosine x is? Take the freaking derivative of both sides. So this is going to be a semi-arduous process, just to warn you. It's going to be kind of, okay, we got it. But now to get cosine, derivatives, easy, quick, sweet. Do you see the, yeah. Okay. And again, that is the bare level of why it's important to know how to integrate, differentiate series, power series. Anybody taking diffie-q in your future? Differential equations, sorry. Differential equations? All right, Jeremiah. And a few of you, yes. Okay, good, beautiful. Remember this moment. Think back to this. When you're in differential equations, think back to this moment when I just said power series will be solutions to your differential equations in some instances, right? And then you're going to have to be able to take the derivative and blah, blah, blah. Okay. All right. For us right now, we don't care about that. No, okay. What's that? Okay, gotcha. All right, so that's section 11.9. So then section 11.10. Let's get back into this. And this is what we just barely kind of started to get into last time. So if I write just a general power, in fact, let me do this. Let me start with this. Here's a power series, the most general power series format. And I'm going to say something akin to, I want to build a power series around 3, which means A equals 3. For example, right? Or I can say, I want to build a power series around -2, which means A equals -2, which means this would be x plus 2. Are you guys with me? That's what the phrase is going to be, to construct a power series around something. Okay, so let's do the very first few that we do. Let's make it nice. What's the best value for A? 0. I love it. So let's do that. And this officially is called a MacLaurin series, which I'm going to completely misspell, because I don't know how to spell MacLaurin. Blah, blah, blah. I almost got it. Nah. It's always, is it MC or is it MAC? Never. So MacLaurin series are when A equals 0. General Taylor series is when A not equal to 0. So MacLaurin really is just a specific instance of a Taylor series. Why do we give them separate names? Why don't we just call them all Taylor? Because this guy discovered this shit at the same time this guy discovered this shit. So we give them both props, right? He didn't build off of him. He did the work. They each get their own props. Okay. Maybe. Okay, so let's not do Taylor yet. Let's stick with MacLaurin for the moment. Which means the form of it's going to be this. So we feel we've seen several examples of a function that could be written as an infinite series, right? 1 over 1 minus x equals some x, and then we did the derivatives and blah, 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 right? We know this is possible. So now we're going to say, okay, we lucked into that shit, but can we develop a process so that if somebody gives me a function, can I put it into this form? Okay, I like it. And again, why is this good? Because I can have some funky ass function and I can make it into a polynomial, and I might only need 3 of the elements to get close enough to the actual answer, right? And a second degree polynomial is way better than 1 over natural log of square root of x plus 2. And, yes? I would much rather work with a quadratic than with freaking 1 over the square root of natural log of, yes? Okay. Okay. So, what do I have? Okay. That weird color. Oh, no. Okay, you want. So here's the idea. If I'm given an f of x and I want to put it into this form, so let's really write what this thing looks like. This looks like C0, right? When n equals 0, I get C0, x to the 0, plus C1, x, plus C2, x squared, plus C3, x to the third, forever. Yes? Okay. So what we want to do is if I have f of x, I want it to equal this at 0. So a equals 0. So I'm given some f of x. What will f of a be? F of 0. Well, if I'm assuming I can put it in this form, what will f of 0 have to be? So here's I kind of did that quickly. I'm going to assume I can put the function in this form. And now I'm going to start to see what's required for that to happen. So what will f of 0 be?
Just 0.
No?
Oh, C of
C0, right? Okay. That's why when we said just 0, I was like, did you say no? Okay. Do you guys all see that? If I put a 0 into this, I get C0, correct?
Yeah.
Okay, I like it. Now, if I do f prime of a, well, let's see. Let's do some work over here. And let me turn this little dude. Let's do some work over here. This is f of x. What is f prime of x? Just this polynomial here, right? F of x is this, is that. So what's f prime? What's the derivative of a constant?
C1.
Yeah, derivative of c1x will be c1. Derivative of c2x squared is
C2x.
2 c2x,
Oh,
right?
Oh, yeah.
Derivative of c3x cubed.
3C3x squared.
Okay, I love it. Let's do one more.
6C4 x cubed.
No, I'm sorry.
Oh.
Not one more derivative, one more term.
Oh.
4c4x cubed. Is that cool?
Yeah.
Plus blah, 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 forever. Stop for a minute. So what now will f prime of 0 be? C1. I like it. What we are doing, I want you to realize, do you see how every derivative I do is going to be equal to some function of Cn, C something, yes? You start to see that? So we are constructing, so now, for example, C0 is f of 0. C1 is f prime of 0. So given a function, I put f of 0 here. I put f prime of 0 there. That's what we just figured out. Now let's keep going. What's f double prime of a? Well, now I need the second derivative. So f double prime. C1 goes away. I get 2c2 plus 6c3x plus 12c4x squared, blah, 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 blah. Right? Go with me. We are creating the function Cn. We are determining what our coefficients need to be for this to work. For 1 over 1 minus x, the coefficients were all 1. In fact, we'll go back. We'll actually, the first thing we'll do is when I get all this shit down, we'll go back and construct the series for 1 over 1 minus x and show you we get the same damn series. If we don't, we can throw it all out. We can forget about the rest of chapter 11, and we can go wherever the hell we want to. Right? So this is where you go, please make a mistake, Jeff. Am I getting this ahead of myself? I haven't done this yet, have I? So what's f double prime of 0? I think you already said it. 2c2. So for example, c0 is f0. F of 0. C1 is f prime of 0. C2 will be f double prime of 0 divided by 2. You can see I can solve for the c's. Yes? So one big thing, what is the only thing in a power series that we don't know? Yeah, we get to pick x, yes? So if you say we don't know x, you're wrong. We pick x. We can pick whatever that is. N is defined already. The only thing we don't know is Cn. So what are we doing right now? We're constructing Cn. Whatever function they give me, I can figure out what CO is. I just plug a 0 into f. Figure out what C1 is, plug a 0 into f prime. Figure out what C2 is, plug a 0 into f double prime divided by 2. I'll just do one more of these and you'll start to see a pattern. F triple prime, this goes away. 6c3 plus 24c4x plus bullshit. Okay, right. So pretty cool. Every term has an x in it except for the first one. So now f triple prime of 0 is going to be 6c3. What pattern is happening with the coefficients here? It's a factorial, of course, right? The next one's going to be 21. Why is it a factorial? Because the powers go up by 1. So as they come down, they keep making a factorial. You can see that. This started off as 1, right? Then it was 4. Now it's going to become, well, let me see if I can follow myself. 4, and then it's 12, and then it's 24. So 24 is 4 factorial. 4 times 3 times 2 times 1, right? Okay, so. By the way, we're constructing the process. You're never going to have to do what I just did. We're constructing what we will do, right? So this is sort of like the derivation phase. The making the stuff, right? We're making the stuff. So you still have to wait and see what the nuts and bolts are going to be of what you're going to do. So let's collect what we know. We know this. Given f of x, find the first two derivatives of f of x. Then C0 will be f of 0. C1 will be f prime of 0. C2 will be f double prime of 0 over 2. C3 will be
f triple prime 0 over 6.
6. Do you guys know how to do the fourth derivative, by the way? Do you guys all know? The first derivative of s prime, second is f double prime, third is f triple prime. Do you want to keep doing primes forever? The 80th prime? Just a minute. Do you guys know how to write, well, how would I write the 80th prime? Anybody know?
F-I-V.
Say again?
I-V.
No.
Roman numeral.
I like it, but no. Because Roman numerals get sucky too. Then it would look like the end of a movie. MCM, XLI, right? So I do this. That's all. That's the 80th derivative. So C4, what do you think C4 is going to be? We didn't even do it, but what do you think it's going to be? F4 of 0 divided by, good, times 3 times 4. So what is Cn going to be? Which derivative? Nth derivative divided by n factorial. Can we stop? Yes.
So if Cn is a sequence, is it always going to be a factorial?
For this, yes. In general, it can be whatever the hell it wants to be.
So if, like, for all power series, or is it? So for all power series, when you.
So let me answer that question in an interesting way.
Alright.
The CNs, this is the definition of the CNs for any MacLaurin series. You be very careful. This is specifically for a MacLaurin series, right? All of this is for MacLaurin. It's going to change a little tiny bit for Taylor. I'm just going to have to put the minus A shit in there, right? And then here, instead of 0, it'll be whatever the hell A is. Is that cool? Because in this case, what's MacLaurin mean? A is 0. So for Taylor, it's going to be A is not 0, something else. Okay. In which case, I would just put an A here to be more general, right? Okay. I want you to understand, whatever my function is it possible that the derivatives of the function itself has an n factorial in it? The answer is yes. So, if this has an n factorial in it, won't those cancel? If fn0 is equal to n factorial times shit, won't the n factorials cancel? So, your end result might not have an n factorial. But at this stage, this is what it always is for MacLaurin. Cn is always this for MacLaurin series. When you start putting stuff together, maybe that doesn't bear out. Now listen, I know what Cn is. What is it I'm really trying to get? Cn was necessary for me to construct this guy. Don't I want this guy? No? Yes?
Yeah.
No? You guys are all like, I just want to go. That's what I want, Jeff. No. So we've given a function. We want to know if we can build a power series. I pointed out that this is the only piece we don't know. We control x. N is already controlled. Cn is the only thing we don't know. We just constructed them. So, has everybody got this captured? All right, so here's the end result. Here's where we ended up, and then we'll do a nice concrete freaking example, yes?
Yeah.
Okay, I guess so, okay. If you need it, I guess so. I'm gonna erase this, you ready? Okay. All right. Oh my God, what property? I don't know. So now we know f of x equals the sum Cn x to the n equals the sum n equals 0 to infinity f n 0 over n factorial x to the n. That's for MacLaurin. Now I understand, I can almost read your thoughts right now. You're like, okay, sure. What do I do with that? Okay. Let's do, yeah, I guess I could start with that one. Sure, why not? So let's say, yeah, let's go ahead and do, I'll actually stick to my promise. I'll see what that feels like. Let's do this one. So let's build a MacLaurin series for this function. Now we already know the answer, right? So now we're just going to verify the answer. We're going to verify this process seems to work. Because we better get what we know is true. Okay. And now I'm like, I didn't do this before class, so shit, here we go. So the very first thing you should do is just make a series of derivatives. So what's f prime? We did this earlier, right? 1 over 1 minus x squared, right? And again, there's a negative power on this, but there's also a negative chain rule piece. That's why it's still positive. What's f double prime? Yeah, so now there's a negative 2, but there's still a negative chain rule, right? So there will be a negative 2 that comes down, but then times the negative 1. So now it's 2 over 1 minus x cubed. Does everybody equal that?
Yeah.
And let's do the, let's go to the third, let's see.
It's 6 now.
6 over 4.
Yeah.
All right. Is that enough? Can you guys, I don't have to do the work now to figure out the fourth one, do I? I can just follow the pattern that I see. Can you see that? So could somebody go that extra step and tell me what the hell this is? I'm sorry, we're not there yet. Let's figure out the zeros. What's f of 0? 1. What's f prime of 0? 1. What's f double prime of 0? 2. What's f triple prime of 0? 6. I like it. So what do you think f 4, 0? Yeah, it's going to be 24, of course, right? Is this a perfect factorial thing? Yes? You guys see that?
Yeah.
What's 0 factorial?
1.
1 factorial.
1.
2 factorial. Yeah, okay. Just make sure it does go 1, 1, because 0 is equal to 1 factorial. 0 factorial is equal to 1 factorial.
So can I ask you, is it just move from 1 to 1? How is it factorial?
Say again?
From the
What's 0 factorial? In fact, how many derivatives have it taken at this point? 0. So that's the 0th term. Yes? That's the first term. 0th term. N equals 1. So n equals 0, n equals 1, n equals 2. What is 0 factorial? We talked about this. Didn't we? I think so. Yes, thank you. Somebody out there is like this. Yeah, we talked about it. I agree. Maybe? No? All right, what do we say? It's 1. And how did we prove it? Real quick. What's 3 factorial? 3 times 2 times 1. What's 2 factorial? It's 3 factorial divided by 3, which is 2 times 1. What's 1 factorial? It's 2 factorial divided by 2. Yes? Which is 2 times 1 divided by 2 is 1. What's 0 factorial then? 1 factorial divided by 1. 1. Yay. So it's not just defined to be 1. It is 1. Okay. So what the shit does all this mean, Jeff? I don't know. All right. What then is fn of 0? Now we're ready for it. You can do it. What's f0 of 0? The 0th derivative at 0 is 0 factorial. The first derivative of 0 is 1 factorial. The second derivative is 2 factorial. The third derivative is 3 factorial. So what's the nth derivative at 0? N factorial. That's going to be the most exciting part for you. It's going to be trying to determine the pattern here to figure out the nth derivative. Right? Yes?
So if f to the n of 0 is n factorial, then you plug that back in at the top.
There we go.
Factorial
There we go.
Over n fact, is that just 1?
So now we're able to continue exactly what I was saying earlier. I love it. So now we got all this beautiful work here. Now I can take this. Fn0 is n factorial over n factorial, x to the n. Is this the same series?
Yeah.
Then 1 over 1 minus x was equal to? Yes, it is, totally. So, too bad. We keep chapter 11. Maybe. The worst part about this whole process, and you don't know yet, you're like, the whole thing is bad. The worst part is going to be figuring out this pattern. This one was pretty damn straightforward. They are not all going to be as straightforward. Now, thankfully, let me ask you this. If I ask you to create the third MacLaurin polynomial, okay, what that means is I want you to go out to the third term in the series, and that's all I care about. So if the question in the homework says, find the 6th Taylor polynomial, or find the 7th MacLaurin, you only have to do that many. You don't have to do this step, because you don't care about the nth then. You only care about the first so many. And then I could just see here, what's it going to be? It's going to be, I can just start plugging stuff in and seeing what it is, right? Okay. Maybe. So I would do like 1 over 1 factorial times x to the 0. I'm sorry, 0 factorial of x to the 0. And then 1 over 1 factorial x to the 1. And then 2 over 2 factorial. And so those would cancel. You would just get 1 plus x squared plus x cubed. Okay. Oh, plus x squared, sorry. Okay. So let's try a brand new function. I could ask you, well, let's see. What do you think is a function you would want to look at? What's a function that's not that terrible? And don't tell me, what would be silly about trying to do any polynomial to find the Taylor or MacLaurin series for a polynomial? Why would that be silly? Because we're trying to take a function and make it into a polynomial, aren't we? So I already know what the polynomial is for a polynomial. So don't tell me I want to do x squared plus 1. Because I'll say x squared plus 1, done, next. Does it make sense? Yeah. In fact, how many derivatives do I do of x squared until it becomes 0 forever? 1 derivative of x squared is x, second derivative is 1, third derivative, 0. So I do 3 derivatives, and it's 0 forever. Do you guys understand? So would it really be an infinite thing? No, because there's already x squared plus 1. I know it ends. It's not an infinite polynomial. So let me give us the function, because I don't know what you guys would say. Well, you want to be nice to yourself. Let's do sine x. Yeah?
Yeah.
Okay. Let's do sine x. Let's see what the shit that is. And then we can get closer to my shirt, right? The shirt that I wear that's got the e to the I pi. I'll be one step closer to proving that thing. Okay. So you guys, can you start doing the first few steps? Meaning, just calculate a few, well, I mean, that's kind of silly. F of x is sine x. What's f prime? Cosine x. What's f double prime? Negative sine x. What's f triple prime? Negative cosine x. What's f for sine x? Okay. Excited. So what is f of 0? So we're doing a MacLaurin series for sine. F of 0 is 0. F of 1 is, I'm sorry, f prime of 0 is 1. See where my brain went. F double prime of 0 is 0. F third of 0 is negative 1. Zero. Okay. So every even derivative is going to have a value at 0 of 0, right? Okay. So that's kind of a strange thing so far, but it's kind of beautiful because, what, for example, f5, the fifth derivative of x, what is it at 0 then? It's 1 again now, right? So it looks like if I ignore all the even derivatives, which means which powers of x are going to be missing from the polynomial version of sine? I'm ignoring all the even derivatives.
What was the question?
Which powers of x? Okay, let's just construct it. I'm not going to have a first term, correct? It's going to be 0. I am going to have this. What's the power going to be for this one? What's n here? And the funny thing is, n is equal to the number of derivatives you've done, right? So the first derivative, so I'm going to have an x to the first. I'm not going to have an x squared. I am going to have an x cubed. I'm not going to have an x to the fourth. I am going to have an x to the fifth. You guys see that? Okay. So all the even derivatives are 0, so all the even powers will have 0 coefficients. They won't be there. So let's write a few terms out. Let's see. Well, so here's the weird thing. If I try to do this, that's hard to say, yeah? Okay, so let's do this. What if I do this? What do you guys think about this? Jeff? Anybody understand what that means? If n is 0, that's the 0th derivative. I haven't taken any derivative. If n is 1, second derivative. Yes? So every single one of those is?
Even. Or maybe not.
All the even derivatives are 0. Okay. So what's the more interesting thing to look at? The odd derivatives. What are they?
1 or negative.
Yeah, so it's -1 to the.
Oh, it's an alternate?
So when n is, yes, when n is 1, when n is 0, I get the first one. That's what I'm trying to say. Right? When n is 0, I get the first thing. Right? And the power and the sign is positive. Yes. When n is 1, I get the third one, and the sign is negative. Yes. You guys with me? So this should be -1 to the n. Yeah. Okay, maybe. So let's do this. Can you guys tell me? Let's try this. Can you guys tell me a few terms here? So for example, let's just write a few terms out. So this will be when n is 0, it's f of 0 over 0 factorial x to the 0. Let's just write a few of these. Really write them out. 1 factorial x to the first. Is this cool? I'm just totally just putting values of n in. And then I'm going to worry about what it is. F double prime of 0 over 2 factorial x squared plus triple prime of 0 over 3 factorial x cubed plus, let's just do up to 4. I think that's plenty. Of course, it keeps going. So every other one, of course, is going to be 0. So this is 0 because f of 0 is 0, right? Okay, so that's 0. So what's this? F prime of 0 is 1. 1 over 1 is 1, so I get x. This is 0, because f double prime of 0 is 0 again. Every even derivative is 0. So then I get this one. What's the third derivative of 0? -1. So I'll get minus 1 over 3 factorial. Yeah. So I get this. X cubed over 3 factorial. Okay. Now I could make 3 factorial 6, but you'll see why I'm not doing that yet. Let's go out to the next one that exists, which would be the fifth one, right? F5, 0 over 5 factorial x to the fifth. Okay. So what's F5? If the fifth derivative is at 0, is 1. So I get plus x to the fifth over 5 factorial. Let me stop for a minute. Can you guys see the pattern for this series? What's it going to be? You can start at whatever n you want to.
And 0. Or,
Alright, so if you want to start at 0, that's you can. Let's see what happens. So I need,
so it's x.
so this is when n equals 0.
X to the 2n plus 1.
All right.
N factorial.
Good, because that'll give me 1x, yes? And it will also give me 3 would be next, 5, because 2n plus 1 is a general odd number. And what's beautiful is, isn't this over 0 factorial? Or in fact, 1 factorial is even better. There you go. Right? And then 3 factorial, 5 factorial. So the power and the factorial are the same. So whatever we use for the power is the same for the factorial. They're the same numbers in each term. Yes? That is what sine x looks like. Yes?
Do you need to make it alternating? Because that one's minus. And
Oh yeah,
one's
yeah.
plus.
I forgot the negative stuff. Thank you. So then looking at the alternating stuff, what would that be? I want the first term to be positive, so when n is 0, I want it positive, so I can just do to the nth power, which is really what we figured out here. Yeah. Thank you. How would you then, so now you really understand what I said earlier. We could put cosine here. And then do derivative, and then f and then put this and then. How would you rather figure out what cosine x?
Take the derivative.
I'd rather take the derivative, right? So once you create a few functions, you can then figure out all of those series for the derivatives and the integrals for that function. Kind of crazy, right? So what's cosine x going to be then? Let's see. Take the derivative of this thing. You can do it. You can do it. I know you can do it.
2n plus 1.
Good. So the negative 1 to the end is still there, right?
Yeah, so with the 1.
2n plus 1 comes down in front of this, so now it's what power?
2n.
2n, good, because you just lost 1, right?
And then just over the same.
Over 2n plus 1 factorial, but of course you realize that'll cancel there, right?
I didn't realize that's the things.
No part. No. It's part of why I'm here. You guys all see what just happened? Right? And now I can let n equal 0 because the first thing is not 0. So see what this looks like in terms of, in polynomial form, right? Infinite polynomial form. What's it look like? When n is 0, what do I get? So this is for sine. For n equals 0, what do I get? X to the 0 is
1.
1.
1 over
2 times 0 factorial is,
so 1 over 1.
I'm sorry, I should be 2n factorial. So 0 factorial is 1, so I get 1. When n equals 1, this is being minus, yes? X squared over 2 factorial. In fact, let me do it like this. 2 factorial is 2, right? But let me just do this. I want to show you something really kind of cool. Are you guys all with me? I'm just plugging the eyes of n in. N equals 2. Now it's positive again. And negative 1 squared. X to the 4th over 4 factorial. Because again, the powers and the factorials here are the same number. Do you guys see, if I say this, are you cool with this? Do you see how cosine is all the parts that sine is missing? Do you see how it's missing a constant? Do you see how it's missing a squared? Do you see how it's missing a and that kind of? So it seems like, we're not going to do this today, don't freak out. Doesn't it seem as if I should be able to kind of combine them to make something else? Yeah? What time is it? Oh, we got time. Ooh, it's too bad for you. All right. What I want you to do, let's see if you guys can do this. I want you to try to do everything we just did for 1 over 1 minus x and for sine x. I want you to do it for e to the x. Yes? So you're going to have e to the x. Okay, well, that's good. Start. We're going to build, it's still MacLaurin. So next time we'll get into Taylor. It's just gonna be like a little adjustment to our MacLaurin stuff. So I wanna do f of x equals e to the x. So try to do the steps, see how far you can make it. And then I'll come in and try to catch up to you. How you doing? No. Yes? You guys I mean,
Yeah.
oh, right? So f of 0 is 1. F prime of 0 is 1. F n of 0 is 1. Right? Does everybody agree? E is its own derivative forever, and e to the 0 is 1, so it's 1 forever. That's okay. That pattern is freaking beautiful, right? It's just always freaking 1. So if I put this together now, see, I want to keep this up here. If I put it in here, I'm going to get, it's going to be 1, and let me put the x to the n on top. You guys remember seeing this before?
Oh, yeah.
That should look vaguely familiar. I think I said something when we looked at it, like, this is important, I get it. We did its interval convergence, and it had an infinite, if I remember correctly, infinite interval convergence.
Yeah.
Interval convergence, okay. Write out a few elements for me, let's see. When n is 0, oh my God, what is in here? Do I need more or less? I'm gonna say more, okay. No, officer, I'm fine. When n is 0, what do I get? 1, does everybody recall that, right? When n is 1, what do I get? X. When n is 2, right? I'm going to put that factorial just for a minute, right? It is 2. And then x cubed. Does anyone see how this is almost sine x plus cosine x? Do you guys see that? It's off by what? Yeah, there's negatives where there shouldn't be. Okay. But do you see how if we do some adjustments to this, we should be able to kind of combine them to make this. Somehow, some multiple of sine plus some multiple cosine equals freaking e to the x. Is that something you would have ever thought was possible? Ain't no way we would have said, well, yeah, e to the x is cosine x plus sine x. No way. Right? Please see, this is so cool as shit. So, somebody said, why do we have series? Okay, so I gave the most basic, boring shit, right? It's still good shit. But this, holy crap, you start to see connections between functions you could never see. And then you start to realize, for example, how important complex numbers are. Because very often, as students and very often as teachers, we neglect to talk about complex numbers. In fact, it's just not part of the curriculum, unfortunately. But, you know, good old Jeff, I'm going to bring him back. Because remember on the shirt, it was e to the I pi, right? Which, if any of you are curious, that kind of gives you an idea of what we're going to do with some of this stuff. Okay. By the way, last thing for today. Here we're now. E to the x equals this. Yes, that's what we just proved. We just proved that e to the x can be expressed as this power series. Now, real quick, I haven't talked about this yet. I'm not going to talk about it right now. Can I make a power series for any function? No. So we still need to talk about what's got to be true in order for a power series representation to actually equal the function itself. That's not always true, but it's only not true for the most freaky ass functions, really. So, but we'll still talk about it. Real quick, remind me, what would e to the 2x be? Not a big deal.
2x to the n.
Be more specific. What do we mean by that? Do we mean this?
No, like.
No, good. Okay.
Over,
It's just whatever the hell's here. It's like any function. Whatever's where x is, put it where x is. Isn't that crazy? So what's e to the negative x? In fact, let me put this up here. Sorry, I'm getting way down there. What's e to the negative x going to be?
Parentheses negative x to the n over n factorial.
Yeah, it'll be negative x to the n, n factorial, which you can write instead as negative 1 to the n, x to the n over n factorial. Nice alternating series, right? So again, integration, differentiation, create new power series. In fact, the derivative of e to the x is supposed to be itself, yes? So we could actually do that. I'm not going to do it right now, but you can do it and actually show, yes, it's its own derivative. But also, just plugging other things in where x is, you create new functions. You create new power series for those functions. Okay, so what we're going to do next time. Tonight was a bunch of me talking. Next time is going to be a bunch of me letting you do some problems on your own, right? So I'd say for homework, you should be getting into 11.9. If you haven't gotten there yet, you should be getting into it soon, right? Over this weekend, maybe. The quiz is only up through 11.8, so you do have time to get into 11.9. You want to focus, get through 11.8 for sure by Monday. So on Monday, we'll do the quiz, and then we'll do this handout together, and then I'll give out the practice test, and Wednesday is review day. Okay. Thank you for humoring me. I'll see you guys. Let me know if you have any questions.